Okay. So we're going to take a quick quiz over identities and equations before we get going today. So get out a piece of paper. And at the top of this, if you would put quiz 2, week 3, you can't see that, but that's what that should say. Quiz 2, week 3, there's 5 questions. The first 2, I need you to simplify. Second one, I want you to verify that identity. And then the last 2, I want you to solve the equations. Okay, you got about 5 minutes left. you're done, I need you to just turn it in, please. Up here at my desk. Bring it up to me.
I couldn't get those things, so there's no.
I don't know. It doesn't matter. Let's go for it. Come around this side so we don't mess with the focus, autofocus we got going on. All right, hand it in for me, please. All right, did I get all of them? What are you supposed to do on the very first one? Distribute, all right, I will. You would get cosine times secant x, right? Minus cosine squared x. What's cosine times secant? So now we have 1 minus cosine squared x, which is what? Sine squared x, very good. What would you do for question number 2? Does that one look somewhat familiar to you? What is our common denominator?
1 plus sine x plus 1 minus sine.
It's the 2 denominators, isn't it? 1 plus sine x and 1 minus sine x. Okay, does it look familiar to you, that one?
Yeah.
Close, right? You had a problem like that on your Desmos activity and a problem like that in the homework assignments. What side would you start on to verify that identity right there? The left-hand side, that's right. And what might we do there? What is cosine times secant? Now I have cosecant squared minus 1. That is cotangent squared, isn't it? Okay, good. Now, how about question number 4? What's the first thing you would do there? Okay, so I'm going to add 1 to the right-hand side and then divide by 2. So I'm left with cosine 2x is equal to 1/2, positive 1/2, yep. And then we would have to go around twice though, because it's a double angle, isn't it? Okay. What about the last one right there? Can you factor that? Yes, you can factor that. Okay. All right, practice, keep practicing. All right, keep practicing those problems. This unit right here, the one that we are going through with the identities. Verifying identities, fundamental identities, and solving trig equations is generally the most difficult of the whole thing. Like in my 16-week trig class that I teach, that's the chapter that's the hardest. Okay, so it'll only get easier from here. Keep thinking that, all right? Keep thinking that it'll get easier, because it does. So we're gonna talk today about another set of identities that we're gonna add to our growing list of identities that we're working with. So if you have a list of identities that you have written down, get that list out and add this to it, okay? Because we're gonna talk about the sum of difference identities for cosine, sine, and tangent. And we've separated them out, or I've separated them out here, because I'm gonna deal with them individually. So what we're looking at here in this first few examples has to do with the sum or difference identity for cosine, okay? What it says is that if I have the cosine of two angles A and B, A plus B here, all right? We can't just use the distributive property on this. That does not apply because our angles A and B are kind of like hidden inside of the trig function. Okay, so I can't distribute into it. That property doesn't work. So when that doesn't work, we have this identity that we're going to use. And this identity says, and you'll notice that cosine, pay attention to the plus and minuses here. So what I have is the cosine of angles A plus B is equal to the cosine of angle A times the cosine of angle B minus the sine of angle A times the sine of angle B. Okay, remember we're dealing with right triangles here. These two angles A and B would typically be, you know, acute angles, right? And then when we do the difference identity for cosine, it's pretty much the same thing. You have the cosine of A and B plus the sine of A and B. Okay. And when we are dealing with this to apply, let's say, this identity, let's look at this first example that I have right here, where I want to know what is the cosine. I want to know the exact value, which is not going to come from my calculator, right? It's going to have some sort of square root probably in it or something like that. I want to know what is the exact value of the cosine of negative 75. Now, if you think about it, do I have an angle that is off of the unit circle that's equal to negative 75? No. So we don't know what the exact value is. But we can find the exact value by saying, well, are there two angles that add together to give me 75 that I know off of the unit circle? And yes, there are. All right, there are multiple different ways for us to consider this, but I want to talk about it in terms of the angles. So the cosine of negative 45 plus negative 30. Those two angles add together to give me negative 75, don't they? And I know those two angles exist off of the unit circle. So you're going to pick angles that exist off the unit circle and figure out how can I combine them, either adding or subtracting, to come up with the angle we're looking for. And now we just apply this identity, which says, okay, I'm going to take the cosine of the first angle, negative 45, times the cosine of the second angle, negative 30, minus the sine of the first angle, negative 45, times the sine of negative 30. Now, each of these pieces here, I can evaluate, right? I know what the cosine of negative 45 is, right? The cosine of negative 45 is positive, let's do square root of 2 over 2. What is the cosine of negative 30? What quadrant am I in? Fourth quadrant. Cosine of square root of 3 over negative 30 is what? Square root of 3 over 2, that's right. Minus, now what is the sine of negative 45? Negative square root of 2 over 2, and the sine of negative 30. Negative 1/2, right? This is why we have to know the unit circle, okay? Minus 1/2. Okay, So what you want to do is we're applying the identity here where I put an arrow, and then we are simplifying each of those components, okay? Students miss the connection here, making our, from each line, it needs to be simplified, right? Simpler. All right, now I'm just going to multiply my fractions. Remember, when we multiply fractions, we multiply numerator to numerator and denominator to denominator. So since both of these are square roots, I can just multiply underneath there and I end up with the square root of 6 over 4. Let's see. Negative and a negative and a negative gives me all, so I have 3 negatives there in that right-hand side, so that gives me a negative. And I would have the square root of 2 over 4.
And that be simplified.
It can't. That's as simplified as it gets. Now, you could write it as the square root of 6 minus the square root of 2 over 4, but that didn't really get me anywhere. Either of those answers would be fine with me. And that's the exact answer right there. Okay? Does anybody think that they want to reach up under there and make that like a total of 8 square roots? Like the square root of 8? Is that what you want to do?
No.
You can't do that, right? That's against the square root rules. That's it. That's all we can do. So you're going to find that when we are simplifying these sum and difference identities, and even the ones we're going to learn tomorrow, you end up with a bunch of stuff that looks like this, right? It looks rather strange, I suppose, right? You would think you could do more with it, but that's it. That is the answer. All right, but that's the exact answer too. Questions on how I applied that? Okay, well, let's get our thinking brains on here for a second. And I want to figure out from the unit circle, maybe this would be better if y'all had your unit circles pulled out. Pull out your unit circle if you don't already have that done. Because it's kind of helpful to stare at it for a second. And collectively, right, with you and a partner somewhere around you, maybe, I want you to figure out, I need 2 numbers that are going to add together to give me 17 pi over 12 from your unit circle, right? Because we can only use values off of the unit circle. What? And there's multiple numbers. Let's do just add. I want to know what 2 numbers add together from the unit circle to give me 17 pi over 12. Just take a second. Use your calculators. Gotta have common denominators. Basically looking for things in terms of 12ths, right? Because I have a 12 for a denominator here. I want to know what numbers add together to give me 17 12ths. Can I change all of those fractions into 12 equivalent fractions? Have we got one yet? What you got?
5 pi over 4 and pi over 6.
5 pi over 4 plus pi over 6. Yes, those 2 fractions will add together to give me 17 pi over 12. All right. Find another set.
11 pi over 6 and 6 pi over 6.
11 pi over 6 and 6 pi over 6. That would give me 17 pi over 6, right?
Oh, yeah.
If I'm adding that right in my head. Okay, but you're on the right track.
But then how'd you get 17 pi over 12 from that?
Change them into common denominators of 12.
What about,
So that would be 10 pi over, no, it'd be 15 pi over 12, right? Plus 2 pi over 12, Javi?
what about 7 pi over 6 and pi over 4?
7 pi over 6 plus pi over 4. Yes, those are two fractions that add together to give me 17 pi over 12. All right? All right. There's one more that I happen to use. Cosine, let's see. 5 pi over 4. That's 5 pi over 4. Plus pi over 6. Oh, that's the same one, right? 5 pi over 4 pi over 6. There is another one. I'm gonna put it up here in case y'all were on that track. 3 pi over 4 plus 2 pi over 3 add to give me 17 pi over 12, okay?
So is it just like,
Any numbers from the unit circle that add together to give me 17 pi over
Right.
12.
what I'm trying to ask is how are you getting it to get the common denominator? Are you just like trying to find the what do you call it? The common multiplier between the 3 pi and the 4?
I don't know that are you asking me how I convert
Yes,
3 pi over 4 into something over 12?
yes,
Yes. What number do I multiply 4 by to get 12?
3.
So I multiply top and bottom by 3 over 3.
Oh, so basically what you do is you just gotta find out what number to multiply to 12 and whatever you do on the bottom, you gotta do on the top.
Yeah, because that's like multiplying by 1.
Okay.
Okay? So the hardest part of this problem is figuring out what two numbers add together to give me 17 pi over 12. Now, could you have gone separately and maybe come up with numbers that subtracted to give you 17 pi over 12? Sure, you can do that too. All right, so there's multiple different ways for us to get a solution here. But now let's move forward. So I'm going to take the cosine then of the first angle, 5 pi over 4, times the cosine of the second angle, pi over 6, minus the sine of the first angle, 5 pi over 4, 5 pi over 4, times the sine of the second angle, pi over 6. What's the cosine of 5 pi? Where is 5 pi over 4? Third quadrant, so this is going to be negative, and what's cosine of negative square root of 2 over 2. Very good. How about cosine pi over 6? Square root of 3 over 2. Minus, what's the sine of 5 pi over 4?
Same thing as your cosine.
Yep. And then how about pi over 6? 1/2, right? Everybody see where those numbers are coming from? Okay, now we simplify. We end up with negative square root of 6 over 4 plus the square root of 2 over 4. It's all variations of that. Okay, it'll always be kind of a combination of those. So that's just us applying this sum identity for cosine. Like I said, the trickiest part of this was to figure out what the two fractions were. Sometimes you'll be given the two fractions in your homework, and sometimes you'll be asked to come up with those yourself.
So where did you get the plus from?
So if you look at the second part of this problem right here, right? That negative times that negative gives me a positive.
Positive, okay.
All right, and that's the exact answer. Let's go backwards. Let's look at this one right here. Cosine 173 plus cosine, or excuse me, times cosine 83 plus sine 173 sine 83. All right, those numbers that I know off of the unit circle, No, okay, but I recognize that I've got the cosine of one angle times the cosine of another angle plus the sine of that first angle times the sine of the second angle. So I have the pattern for the difference identity for cosine, don't I? All right, so this then would have to be the cosine of 173 minus 83, which is the cosine of 90. And I do know the exact value for the cosine of 90, that's 0.
So,
So that's an application of the difference identity for cosine. All right, that's kind of what we're doing here, just kind of messing around with this identity.
that's all you do on that problem?
Yeah, but if the problem said right here, I want to know what that exact value is, and I don't have a calculator, I have an identity, I have a process that I can go through and find that exact value.
Oh, so you just subtract them and then find the cosine of it?
Yep. All right, let's look at this one here. I want to verify this identity. I want to verify the equation is an identity, and we're just going to use part of what we've been doing already. Let's apply that one. I believe this would be on the identity that we have at the beginning, but let's see if we can use our new identity for the, what this be? This would be the sum identity for cosine. So I'm going to start on the left-hand side, and I would have the cosine of pi over 2 times the cosine of x minus the sine of pi over 2 times the sine of x. So I'm starting on the left-hand side here. Now, what's the cosine of pi over 2?
Wouldn't that be, pi over 2, wouldn't that be 1? No, cosine 0.
0, right? So that's going to cause this entire term here on the left to be 0, correct? All right, so now I have 0 minus, what is the sine of pi over 2?
1.
If that's 1, then I now have 0 minus sine x. Well, that's negative sine x, which is now equal to, we can see sine x, the right-hand side. I verified that the identity was in fact an identity using our sum identity for cosine. See what I did? Kind of a short identity. Okay? Okay. Let's add to that list the sum and difference identities for sine. So it's going to be similar, but it's a little different, right? The process will be the similar, but the identity itself is different. So the sine of angles A plus B would be sine of A cosine B plus cosine A sine B. And the difference is sine A cosine B minus cosine A sine B. So you're flip-flopping back and forth between sine and cosine, but the sign, positive versus negative, add, subtract, follows with what you started with. All right, so if we have this expression here, the sine of 15 degrees, and I want to know what is the exact value of the sine of 15. All right, that again is not an angle that I know off of my unit circle. So I'm going to say, do I know two angles that are going to add or subtract to give me 15? Well, 45 minus 30 gives me 15, correct? So now I'm going to apply the difference identity for sine. So that's going to be the sine of the first angle 45 times the cosine of the second, which is 30, minus the cosine of the first times the sine of the second. What's the sine of 45 again? Everybody? All right, square root of 2 over 2. What's the cosine of 30? Square root of 3 over 2. What's the cosine of 45? And the sine of 30? Okay. So we end up with the square root of 6 over 4 minus the square root of 2 over 4.
You just multiply them, right?
I multiplied the fractions, yes. Numerator to numerator, denominator to denominator. Every time. For
That'll be your
signing,
exact answer.
do what?
That would be your exact answer.
That's it. That's the exact answer. Every time we do sines and cosines, it's like we find some, it's just a variation of this that we're looking at, okay? Let's see if we can verify this identity using this new concept, using this new identity that we found. So the sine of x plus y plus the sine of x minus y is equal to 2 sine x cosine y. So let's again start with the left-hand side. Sine of x plus y. That's our new identity we just said. So that's going to be sine x cosine y plus cosine x sine y, right? Correct? That's just an application of our identity we just used. Yes?
Could we also have applied that identity to the other one too, to sine x minus y?
Yep. So now I've got sine x minus y. So sine x cosine y minus cosine x sine y. Now what would we do? All right, I can combine like terms, right? So I have sine x cosine y and another sine x cosine y. So I have a total of 2 sine x cosine y's. And what happened to cosine x sine y?
Wouldn't that other one go away because of that?
Yep, they go away, they subtract themselves out, they cancel each other. And I was asked to prove that the left-hand side was indeed 2 sine x cosine y. So in one line, we did it, right?
That was easy.
Yeah. Okay, so that's just an application of this identity that we're working on. Now the last one, so we've done sine and cosine for sum and difference. This last one is tangent. Tangent is usually a little bit more cumbersome and involved. So what we have here is in the numerator of tangent, we have addition going on between these two things. And in the denominator, we have 1 minus the product. So it's going to be an algebraic mess for a while. We got that written down?
Almost.
Okay. All right, let's apply it. And I'm just gonna tell you that for this number here, the tangent of 13 pi over 12, we're gonna say is you have that much problems with your pen working? Does it lose connection? Yours, Jimmy?
Sometimes. I like it just won't draw in a very specific spot for a bit.
Okay. Scribble, scribble. Tangent of 5 pi over 6 plus pi over 4, add together to give me what we want, the tangent of 13 pi over 12. Okay, so those are the two numbers that I'm dealing with. So since we're doing the sum identity for tangent, this is going to look like the tangent of 5 pi over 6 plus the tangent of pi over 4 divided by 1 minus the tangent of 5 pi over 6 times the tangent of pi over 4. Okay, and now we're going to simplify that. What's the tangent of 5 pi over 6? Everybody? Square root of 3 over 3?
Yeah.
Right, and what quadrant are we in? At 5 pi over 6? Second quadrant, so this is going to be negative square root of 3 over 3. That's the tangent of 5 pi over 6. Negative square root of 3 over 3.
I thought tangent was y over x.
It is. Okay, now what about the tangent of pi over 4?
Duh.
1, right? Oh, it's always a good day when we can find just a regular number like 1, right? Plus 1. All over 1 minus now the square root of 3 over 3, but that was negative. Times 1, right? Because the denominator is the product. Has product in it, I should say. Okay, so far so good? You see what I'm doing here? Yeah, okay. So this looks like negative square root of 3 over 3 plus 1 in the numerator and 1 plus the square root of 3 over 3 in the denominator, right? When I clean it up, when I just simplified the terms, okay, well, there's a couple of different routes you can go from here, but I'm just going to say that I'm going to get rid of the radical, the square root symbol that's in the denominator at this point. All right, and to do that, I am going to multiply top and bottom by 1 minus the square root of 3 over 3. 1 minus the square root of 3 over 3. Remember, we multiply by the conjugate that squares both the first term and the last term, doesn't it? Which is what we want to get rid of
Wait,
the denominator.
Where'd you get the minus from?
It's the conjugate of what we're multiplying by. Remember, the conjugate is the exact same thing as the denominator, opposite sign. That's a conjugate. So if I multiply in the numerator, right? We're gonna FOIL here. So the first term, negative square root of 3/3, times the outer term would be what, plus 3/9. If I multiply fraction to fraction, right, the outer terms together. Yes, shake your heads if you see that. All right, now the inner would be +1, and the last would be minus the square root of 3/3. That's the numerator so far. The denominator is going to be the first term squared minus the last term squared. Well, when I multiply those things together, I get 3/9, which is
1/3.
1/3, and I'll simplify that in a second. So in the numerator, let's clean this up just a little bit here, right? I have negative square root of 3/3 minus the square root of 3/3, so I have a total of 2 of them, don't I?
Yeah.
And here I have 1/3 plus 1. 3/9 is 1/3. What's 1/3 plus 1? 4/3, right?
Is
Okay, so I have 4/3 minus 2 square roots of 3/3 all over 1 minus 1/3, which would be 2/3. So far, so good. You see what I've done right there? Okay, what do you want to go back and look at again?
Well, it's more of just I was confused on combining fraction, things like that.
So those two would be like terms, right?
Yes.
So I have in the numerator, I have a negative square root of 3 minus square root of 3, so I have a total of 2 square roots of 3. Yes. Okay, now I have this complex fraction. What is it? How do I get rid of that complex fraction? Multiply top and bottom by the denominator, 3, right? All right, so I'm going to multiply the numerator by 3 and the denominator by 3. That's still like multiplying by 1. So in the numerator, 4/3 times 3 would just give me 4 minus 2 square roots of 3. So I got rid of the denominators, and in the denominator, I just have 2. Everybody see where I multiplied that? I wanted to clear my equation of fractions, so you multiply by the denominator you're
so
trying to get
basically
rid
all
of.
you did was take away the 3 on the denominator.
Yep, I did it algebraically, right? Okay, and now I can reduce this. One way to look at it would be, this is the same thing as saying 4/2 minus 2 square roots of 3/2, right? I can take that and separate that out. And I can reduce that to get 2 minus the square root of 3.
Is that it, finally?
Finally, that's it. That is the solution to this. That's the exact answer. Tangent is always going to give you a mess like this. When we do the sum and difference identity for tangent, this is what you're going to be messing with. All right? This complex fraction kind of thing. So if you could come up with one of your numbers that you're adding or subtracting together, it could be, you know, like a quadrantal or like, you know, one of the 45s, that's a good day. Okay, if you've got the 30 or the 60 up there in the tangent of 30 or 60, then you've got, you know, all of this lovely stuff to take care of. So that's just algebra, isn't it? That's really just rational fractions, rational functions. Lovely. All right, let's do one that's a little bit more straightforward. How about that one right there? Tell me, you write that problem down and see if you can simplify it. Did everybody see that this is the tangent of 100 minus 70? Or in other words, the tangent of 30. And we know that the tangent of 30 is square root of 3 over 3. So again, just an application of the difference identity for tangent. Okay. Now let's kind of go through some.
Wait, was that it?
Yep, that was it. Remember, we were kind of applying it to simplify it, right? I don't know what the tangent of 100 is, and I don't know what the tangent of 70 is, but I do know what the tangent of 30 is. All right, so in these two problems here, we're going to take what we're given and we're going to write our expression as a function of theta, right? I'm going to write our expression as a function of theta for x in this particular case, okay? And really, it's just, I kind of want to take it out of this trig form, okay? That's what we're looking at here, is this is a trig function of two angles, and I want to rewrite it instead as a function of x. So I'm going to apply the sum identity for sine here. I would have the sine of 5 pi over 6 times the cosine of x plus the cosine of 5 pi over 6 times the sine of x. And that got out of that argument position, in other words, it kind of simply kind of breaks it apart here. Now we're just going to simplify it from here. The sine of 5 pi over 6 is 1/2, right? Okay, so I would have 1/2 times the cosine of x still. And the cosine of 5 pi over 6 is negative square root of 3 over 2 times the sine x that I had.
Wait, what? Oh,
So sine of 5 pi over 6 is 1/2. Cosine of 5 pi over 6 is the square root of 3 over 2. And now we have not a trig function, so to speak. I've got this written more in terms of the variable x is kind of what we're trying to break it out into. Because 5 pi over 6 is negative square root of 3 over 2. Okay, you could leave it there. I would be happy with that. You could also write this as cosine x minus the square root of 3 times sine x all over the single denominator of 2.
Oh, that would
If
work.
you happen to see that as an answer as well. Both of those solutions are perfectly fine to me. Let's see if we can do the same thing, only use tangent, okay?
Easy.
So here I have tangent times theta plus 3 pi. So I want to rewrite this in simplifying it basically, because I have a variable that's kind of hiding in that argument position. What I'm trying to do here is I'm trying to kind of get it out of that argument position. So this is the sum identity for tangent. So the tangent of theta plus the tangent of 3 pi all over 1 minus tan theta times tan 3 pi. What's the tangent of 3 pi? 0. So that's 0, and that is 0. Everywhere I had tan theta, that became 0. So that only leaves tan theta in the numerator over 1 minus 0 in the denominator, or in other words, just tan theta.
that was about the easiest tangent problem on.
That one is pretty easy because there's no fractions, right? So see, whenever you can come up with that quadrantal, it just makes it kind of nice too. So that's 1 minus 0 would just be 1, right? Oh. 0 times tangent would be 0.
Oh, that's okay.
So that's what we're talking about when we want to write this expression as a function of theta or x, right? Something like that. We're simplifying it. Now, another application that we use when we're talking about these identities is in this case right here. So I'm going to work this problem twice, but I'm going to use the same information for it, okay? What we're going to do is we want to find out what the sine of angle u plus v is and what the tangent of angle u plus v is. Okay, so those are the two tasks I'm going to be completing. What I'm told is that the cosine of u is 3/5. The sine of v is 5/13. And u and v, I didn't change my variables there. My angles, u and v, are both in the first quadrant. Okay? So angle u and in angle v are both in the first quadrant. This is where we're going to come in and remember that in order to take the sine of u plus v, in fact, let's come down here actually. Let's come down here and look at this first so we can see. When I take the sine of u plus v, it's going to be the sine of u times the cosine of v plus the cosine of u times the sine of v, right? That's just applying the sum identity for sine. Did I miss anything? Sine of the first, cosine of the second, cosine of the first times the sine of the second, right? Okay. So I'm only given the cosine of u, so I have that one, and the sine of v. So I'm going to have to go in and figure out what these other angles are. And while I'm at it, let's go over here, and I just want to address the tangent of u plus v. Tangent says I'm going to take the tangent of angle u plus the tangent of angle v and divide that by 1 minus tan u tan v. So I'm going to have to know, if you're paying attention to this, I now have to know sine, cosine, and tangent for angle u to apply it to this stuff. And I have to know sine, cosine, and tangent of angle v, don't I? I need all of those components. And we can do that. Let's go back to our definition of our trig functions, x, y, and r, right? I know that cosine of u is defined as, or cosine of theta is defined as x, which would be 3, r, which is 5. Therefore, y has to be what, everybody? Yeah, y has to be 4, right? It's a 3, 4, 5 triangle, correct? Okay. And therefore, I know that the sine of angle u is 4/5. We already know the cosine of angle u is 3/5. And the tangent of angle u is 4/3, correct? Okay. Let's do the same thing for angle v. By definition, I know y is equal to 5, r is equal to 13. What does x have to be? 12. This is another special triangle. Y'all need to know those special triangles. It's all in quadrant 1, so that's why all of our positive versus, it's all going to be positive, isn't it? So I have the sine of angle v again is 5/13. Cosine angle v is 12/13. Tangent angle v is 5/12. That's nothing that is new, right? That's the same thing that you just had a test on, right? Okay, but we're gonna use each of those components to now figure out what the sine of u plus v is. So I know that the sine of u, what is the sine of u?
Sine of u is 4/5.
I'm gonna replace sine u with 4/5. What's cosine v? 12/13. Okay, what's cosine u? 3/5. What's sine v? Okay. Now we're going to add these two things together, or multiply and then add. So once you add those numbers together, remember you're going to multiply numerator to numerator to denominator, add them together. Okay, and you end up with 63/65. Make sure you can get that answer. Probably going to need your calculator.
Oh, this is easy.
It's just putting the pieces in the right spot, right? You just had to have all the puzzle pieces in order to apply it to the identity. All right, so you should get 63/65. See if you can now come up with tangent. Because we have everything we need for tangent as well.
Yes.
Okay, did you get 63/16?
Yes, ma'am.
Make sure you can get 63/16. This is a kind of a calculator skills problem at this point. Depends on, how much you like to throw in your calculator, how well can you work with parentheses, Some people don't, some people can come here and do it just like I have it written, where you're gonna surround the numerator and the denominator. Some people like to break it down a little further, so I would have, 7/4 divided by 4/9. Do it from there. You can get that, you can probably do it in your head. Okay,
Where'd you get 7/4?
I added the numerator together, and in the denominator, I added the denominator together.
3 + 12, that'd be 50. Oh, okay. you said
Okay.
divide.
Okay. So that is our application, right? Where I am asking you, and you will see this on a test, I guarantee it, that type of a question right there. And you're gonna apply the various identities that we're working through today and tomorrow. All right, sine, cosine, tangent, sum and difference, and so forth. Okay,
How'd you get 7?
I'll show you later, Javi. Okay. Let's look at this one. This one is, so now that we know kind of what we were doing with actual numbers, let's see if we can do it with some algebra. okay? So this says the sine of arctan 2x minus arc cosine x. And I want to write this as an algebraic expression. Anytime you see that, that means that this is just going to turn out to be a bunch of letters, right? Algebraic expression. But I've got the sine of, remember that when we take the inverse, that's an angle, right? The inverse function is an angle. And this one in here, so the arctan of 2x is some angle. Arc cosine of x is just another angle, right? So I'm looking now at the sine of these two angles that I'm subtracting here. So we're going to apply our sum, our difference identity for sine. So this is going to be the sine of the first angle, which I'm going to rewrite as inverse tan 2x times the cosine of the second angle, which is inverse cosine x, minus the cosine of that first angle, which was inverse tan 2x, times the sine of the second angle, which is inverse cosine x. Now I want us to focus just here on this first part of that expression, right? The sine of the inverse tangent of 2x. Remember when we worked problems like that on the homework or on that section for inverse functions? And we said, okay, well, if I'm trying to simplify this here, I'm going to let theta be equal to the inverse tangent of 2x, and therefore tangent of theta has to be equal to 2x, right? Okay, that was what we did in that section. And now I am trying to simplify this, right? So I have my my tangents defined as my y value, which is 2x, over my x value, which is 1. And I need to know what r is. So if we're thinking about a triangle here, right, where this is theta, the vertical component would be 2x, the horizontal component is 1, and the diagonal component is going to be the square root of x squared plus y squared. Or in other words, 1 plus 4x squared. Correct? Okay. Okay. So that tells me that when tangent of theta is equal to 2x, I have horizontal, vertical, and diagonal components that can be drawn like this. So what I'm interested in then, I'm going to use that to figure out what the sine of theta is. So the sine of theta has to be what? Opposite over hypotenuse, correct? Opposite over hypotenuse, which is 1 plus 4x squared. Now, I can kind of go back to what I'm looking at up here, and I'm eventually going to need to know what the cosine is for the tangent, inverse tangent of 2x, right? So cosine of theta is defined as adjacent over hypotenuse.
So it'd be 1 over 1 plus 4x squared.
1 over the square root of 1 plus 4x squared. That's correct. Remember how before, when we were doing this with real numbers, I had to figure out what sine and cosine were of my two angles? It's all we're doing here, but we're doing it algebraically. So now let's do that same concept with cosine of inverse cosine. Well, I know that those two should give me the value x, but we might need to go a little further. So, yes, Javi?
But we have to try and get rid of that denominator, that radical.
No, we're gonna just leave it for right now. We're not really done with the problem yet. I'm finding all of the pieces to be able to put into this. So now I have theta would be equal to, if I apply this same concept to this cosine times cosine inverse x, I'm just moving over to the next factor here. And I can say, okay, well, if theta is equal to the inverse cosine of x, then cosine theta has to be equal to x, correct? Okay. Cosine's defined as my x component over r. So if I were to sketch that picture here,
R1, what does this say now?
right? So I have the adjacent cosine is my horizontal over my hypotenuse. And therefore, y has to be the square root of r squared minus x squared. Or in other words, 1 minus x squared. And so I can come back and say, okay, well, I already know that the cosine of theta is equal to x. We kind of defined that already. It was pretty easy to see. But sine theta is equal to opposite over hypotenuse, or in other words, the square root of 1 minus x squared. Now I'm going to come back in here because I used color, but I'm going to kind of come back in here and remember how it's easy to see this when this is the sine of angle A minus the sine of angle, or minus sine of A minus B, right? That's how we defined this to begin with. And so for my cosine angle over here, I'm going to just kind of put a little subscript for angle B. That's the theta I'm looking for. So those are different than the angle A's that I'm looking at over here. It kind of gets confusing maybe when you look back on it. All right. Now we have all the pieces to this puzzle. And I am going to go back in and I am going to replace the sine of the inverse tangent of 2x, right? We already know that that's the sine of theta A, yeah? So that's going to be 2x over the square root of 1 plus 4x squared. So it's the sine of angle A times the cosine of angle B plus the cosine of angle A, 1 over
So how
square
does,
root, hold on, Javi, plus 1 over 1, the square root of 1 plus 4x squared times the sine of angle B, which is 1 minus x squared over 1. Can you see why I went back in to kind of remember what my angles were? Sine of angle A, sine of the first angle, times the cosine of the second angle, plus the cosine of the first angle, times the sine of the second angle. You understand where I got each of those components from in that expression that I have so far? Yes, sir.
It would be subtraction, right? Different formula.
Yes, it would be minus.
so how did you get that, how'd you get sine theta A out of sine of the tangent inverse of 2x? I don't get that part.
So I am really calling this angle A, right? So I'm going to say, okay, if this is the substitution that we made when we were talking about inverse functions, I'm gonna let theta A be equal to the inverse tangent of 2x. And therefore, tangent of angle A has to be equal to 2x. And it's that definition that I use to now come up with the components, the vertical, horizontal, and diagonal components. It's the same thing that we did in section, what? 4 something or other, chapter 4, section something or other in the textbook, okay? I'm gonna finish this up and Javi, I can explain it to you a little bit more, all right, after class. All right, does everybody see where these components are at? Okay, let's simplify from here because we're technically not done. Remember, we multiply numerator to numerators. And so I would have 2x squared all over the square root of 1 plus 4x squared minus the square root of 1 minus x squared over that same denominator, 1 plus 4x squared. Because I have common denominators here, I can rewrite this as just a combined numerator 2x squared minus the square root of 1 minus x squared all over the single denominator 1 plus square root of 1 plus 4x squared. That's the algebraic expression. It looks kind of nasty, but what do you do once you've got what do you do once you have fractions, right?
You just fill it all in.
You multiply numerator to numerator, and then you add common numerators together, don't you? And stick it over a single denominator. And we have a common denominator that you can see right there. Okay, yes, ma'am?
Are we allowed to go to the square root of the denominator?
Yes, at this point we can. Okay. Okay, that's kind of an application of our sign, the difference identity for our sign, using our inverse functions before. Okay. All right. Let's solve this equation using our new identities. I have the sine of x plus 6 minus the sine of x minus 7 plus 7 pi over 6 is equal to the square root of 3 over 2. And I am looking for the solutions on the interval between 0 and 2 pi. So we want to simplify this. So on the sine of x plus 6, x plus pi over 6, we're going to simplify to be sine x cosine pi over 6 plus cosine x sine pi over 6. Now let's simplify the second part here. I have minus, and I'm going to put this second part in parentheses. I would have sine x cosine 7 pi over 6 minus cosine x sine 7 pi over 6. And that all equals the square root of 3 over 2. Remember, we're solving this. So let's try to collect and kind of clean up our like terms here. What's the cosine of pi over 6? That's going to be the square root of 3 over 2. What's the sine of pi over 6? 1/2, good. Cosine 7 pi over 6? Negative square root of 3 over 2 because I'm in the third quadrant, and sine of 7 pi over 6, negative 1/2. Okay, so what I've got here is the square root of 3/2 times sine x plus 1/2 cosine x. Now I have minus a negative, which means I have a plus the square root of 3/2 sine x. And I have minus, minus, minus. I have 3 of them.
So wouldn't that be minus again?
Yep, minus 1/2 cosine x is equal to the square root of 3/2. So the cosine x's cancel, leaving me with 2 square roots of 3/2 times sine x is equal to square root of 3/2.
So where did you get the 2 square root of 3/2? You just combine the square roots of 3/2?
Yeah, I collected my like terms. I had
Okay.
counted up how many I had. Okay, so cleaning this up, that cancels, right? This really just gives me the square root of 3 sine x is equal to the square root of 3/2. Now, I want to divide both sides by the square root of 3, correct?
Uh-huh.
So I'm going to multiply both sides by 1/, the square root of 3. And that gives me sine x is equal to 1/2.
Okay, then we can find our,
And so we're only going on the interval between 0 and 2 pi. So I have 2 angles that when I take the sine of them, I get positive 1/2. That would be,
The pi/6,
and what else?
pi/6,
and,
5 pi/6. Okay? So they got longer, didn't they? All right. And the last one that we're going to do together is verifying an identity. So this says that I have the cosine of alpha minus beta over cosine alpha sine beta. And that's equal to tan alpha plus cotangent beta. So if we're practicing with the sum and difference identities here, what side do we want to start with? The left-hand side. So I'm going to apply the difference identity for cosine. What does that give me? Let's expand this out. Tell me what that would be. Cosine alpha, cosine beta, plus
Sine alpha plus
sine alpha, sine beta, all over cosine alpha, sine beta. What do you notice here? I have a single term in the denominator, right? I have a single term in the denominator, and in the numerator, I have addition or subtraction, but I have addition in this case. So that tells me that I can write this as 2 separate fractions. When there's a single term in the denominator, I can separate my numerator. So this is cosine alpha cosine beta over cosine alpha sine beta plus sine alpha sine beta over cosine alpha sine beta. right? I just rewrote this as two separate fractions instead of the combined fraction. What did that gain me? I can cancel common factors now, right? You can only cancel factors. So in the leftmost term, cosine alpha cancels with cosine alpha. And in the rightmost term, sine beta cancels with sine beta. It leaves me, what is cosine beta over sine beta? What's cosine over sine?
Okay.
Cotangent of beta. What's sine alpha over cosine alpha? Tangent alpha, which is what I wanted. Tan alpha plus cotangent beta. Okay. Now I want you to add these 5 problems to your homework set that I know everybody is practicing their homework set. 9, 11, 17, 25, and 65.